All right, have you guys got all your whining and complaining out of your system? No. Well, at least bottle it for right now. So last time, and if you don't have these handouts, I have extra ones over in the bin. If for some reason you weren't here last time, you don't have to get this back out. I just want to refer back to what we were doing. Last time we brought up this unit circle and said that when we deal with triangles, we can actually refer everything back to the unit circle and then scale up from there. You want to do trigonometry, Mr. Cabilo?
I already did my trigonometry a long time.
I still use trig today when I'm like trying to calculate things like how much cable do we need to run up the entire like side of the house for things you cannot measure, like actually take a measure on. Trigonometry is actually really useful in day-to-day life. And guys, I'm literally going to make one of my bulletin boards with a message exchange that I had with a friend of mine this morning that literally said, I used to ask, when are we ever going to use this? And now I use math every day. Like, and it's for like baking and cooking and stuff. No, she is not a teacher.
You're a teacher.
Yeah, that's why she was texting me. No, that she uses math every day.
What does she do?
She's actually a music teacher, but she does a lot of baking and cooking.
Music is very mathematical.
I'm going to move on because arguing with 8th graders is a waste of time. So what was the memory trick for 30, 60, 90 if we're referencing the short leg? Who remembers the values, like the coefficient values that we need to remember for a 30, 60, 90 special right triangle? 2 and the square root of 3. Now you got to ask yourself, which is bigger, the 2 or the square root of 3? But we don't have 3, we have square root of 3. So remember, 2 is bigger than... You guys are starting to get mildly frustrating because I can't get like 3 sentences out. 2 is bigger than radical 3. So remember, that goes to your hypotenuse. If we reference the hypotenuse, those coefficient values get a bit more complicated, right? Now, 45, 45, 90, what was that coefficient value we needed to remember? Not 2. Square root of 2. So be careful. Radical 2 is your multiplier to get to your hypotenuse from your short leg. So then, do you have a question or no? Good, get one. The jar is still there. It's just between the cubbies. It didn't move. It's just a little bit harder to see now. Now, when we don't have right between the cubbies, if it's a snake, it would bite you. Huh? It's a stress banana. The stress banana. These are my prizes that we'll talk about at some point, but if I can never get 3 sentences out, it's going to be hard to end up talking about prizes. Let's head our notes with trigonometric ratios. You can tell that you guys are feeling something because of the math test. You're like, it seems like you're still giving speeches. I love Avi in the back of the room. Hey man, I can throw shade like the best of them. I actually can't help you till... When are you guys out of here? 11:17? Sorry, I have class until 11:17. Oh, just turn it in the bin. So see the turn-in bins over there? You would be... If you're just coming to turn in the paper, then you would just stick it right here. The afternoon at 7. Thank you very much. All right. Do we know why hypotenuse is actually called hypotenuse? If we shift the emphasis of the word, the root of the word is hypo. What's hypo mean? Yes, I don't know what you're doing on your iPad, but it sounds like you should be listening to me. It sounds like I have info that you don't. I I hope you're taking notes. I assume you're taking notes. The hypotenuse is called the hypotenuse because when referred to the right angle, it is beneath it. And remember, in geometry, there's no up or down, so the hypotenuse is the side below. Hypo means below. It's the side below the right angle. So hypotenuse is always the same. It's always the side across from the angle. The issue comes down to when we start using these to talk about our sides. Opposite and adjacent. So if we draw a triangle, and I guess I'll take these notes again with you guys instead of just using yesterday's notes. Everyone draw a right triangle in your paper. It can look like this one if you want. It can be labeled ABC like this one. And if you can like underline hypo on your notes to say it is under. Now really, we often talk about it as across from the 90 degree. But technically why it's called hypotenuse is it's under the 90 degree. Now the next vocab word we need to talk about actually comes with a symbol with it. Anyone ever heard of theta? Okay, what is it? Yeah, it is a reference angle. So theta is the angle that we're looking at that is never the 90. So it's the angle we're working with, or looking at, or calculating with, whatever you want to write. It's the angle that we're dealing. It's the primary angle, but never the 90 degrees. Theta can never be our 90. So it's always going to be one of our acute angles. So here, if we call our theta angle A, let's label that in our circle. Draw a little Easter egg. Right, that's what theta kind of looks like. A little Easter egg. B's on top. Now I'm going to color code these next ones. What does it mean to be adjacent? If I say the neighbor who's adjacent to me and I are going to split a fence, next to all of these things are next to each other, kind of. I mean, there's only three things. They're sort of all next to each other. Next to and touching. So the adjacent side, and guys, like, if you don't pay attention now, you'll end up falling in some trapdoors on Khan Academy, and that's fine, because like you'll learn from that, but I'm trying to help you avoid trapdoors. The adjacent side could be either side. It could be either leg. It depends on what angle we're looking at. So to be adjacent, we look at our theta and we say, what leg is next to and touching? So remember, it's not the hypotenuse, so the leg that is next to and touching. Sorry, I should have put next to, forgot that word. Next to and touching, theta. Which means then, well, opposite here should be the easier word to deal with. Opposite then means opposite the angle we're looking at. So opposite is across. So in this case, BC. It is the side that is not touching the theta. So opposite, I mean, you can say across from theta, if you want to, or whatever will help you remember it. So here's where it gets darn tricky. If B was our theta, and please don't write this because then it would change your notes. So I'm going to say theta like prime, so a different theta. Now AC, which was our adjacent side, now it would be the opposite side. The side that was our opposite side would now be our adjacent side. So if A is your reference angle versus if B becomes your reference angle, oh, maybe I didn't include those. Yeah, so if B is your reference angle, I didn't put the arrows in here, but now AC, and I hate that little menu. I should go into the settings and see if I can make that not happen. AC becomes your opposite, BC becomes your adjacent. Adjacent is always the one that's part of making the angle. It's next to, it's touching. So guys, my neighbor across the street is not adjacent because his property is not touching mine. My neighbor next door to me is adjacent. When we look at these ratios, one thing we said about right triangles, right, is that any right triangles that share the same angles share the same ratios, right? So, well, notice these are similar triangles, right? Like all we did was extend the lines out. You don't need to write this down, but I need you like with me for a second. 6, 8, 10. Wow, that's reminiscent of something else. 6, 8, 10.
Oh, that's the 4, 5. I mean, not 4, 5. 3, 4, 5.
It's the 3, 4, 5. So 6, 8, 10 really came from 3, 4, 5, which means that if I scale up 9, what should I have here? 12, right? Because that's a scaling of 3. If I have my short leg of 12, 16, then what would this be? 20, 15, oh yeah, 20 again because that's the middle leg. I could keep doing this, right? Like all day long. And the other thing I could do is say, well, if all of these come from this base angle of 37 degrees, what's the other angle? I was just going to wave my hands until somebody gave me the answer. So if I can't hear you, sorry, I got this thing and the stuff and the speak up, yell at me. It's okay. I just mean, come on. I go home, my wife yells at me, so it's a joke. Joke. It's a joke. So here's what's cool. Somebody smarter than us. Okay, maybe not smarter than you, but definitely smarter than me. Somebody smarter than me decided if all of these things exist and stay the same, let's formalize it into a table of ratio values. So all of these decimal numbers are fractions. But if we relate the ratio to 1, right, relate a number to 1, you can just actually write it as a decimal. So these are all ratios. So first off, please get with me. This means like 0.57 to 1, right? 0.42 to 1, right? So these are all ratios. So somebody real smart said, hey, with a 55-degree base angle, we would have these ratios between the legs based off the table that we just did, right? But for the angle of 55 degrees. Instead of the angle of 53 that we just did, right? Kind of. We were doing 37, but we could flip things around and do the 53. They did this with every single angle measure. Not just the whole numbers. Every angle. Like, infinitely many, right? No, there are different sizes of infinitely many. So, yeah, and that's a fun argument to have. So, if the ratio between our legs is able to be seen, we can work that backwards and figure out what angle created that ratio. So check it. If we look at a table like this, compared to a triangle like this, and sorry that my little thing is in the way, if we compare 11.9, okay, pretty much 12, with 3.2, what ratio value would that go with here? Yeah, like pretty close to 4, right? That ratio is pretty close to 4, so that would relate to 75 degrees being the angle that created that. Does this make sense? That when we, like, guys, this is like when people joke about using an abacus or old things like that. We're just using a table to do math for us. So an abacus was a thing like you'd move stuff around and like then your answer would, you just like see your answer. Because like it does the math for you. It's like an old-fashioned calculator. That's what this table is doing. Huh? You are correct. The bead thingy.
Oh yeah, that.
So, check it out. We can apply this to any situation, not except. That's the wrong word there. I dislike that now they've changed their hypotenuses to 10. So I want you to visualize with me, instead of 10, if the hypotenuses were 1, then this would be 0.82, 0.57, 0.34, right? Like, so all of these would just be shifted a decimal space over. And then this would relate to the unit circle. Okay, so we can work with 10 right now. That's fine. But if we wanted to relate this to the unit circle, make all the hypotenuses 1. Makes sense? Because the unit circle says the hypotenuse is 1. So here, we have a 35-degree angle. We would match it to which triangle over here? Oh, you had to ask. So, all the triangles that we're looking at right now are right triangles. You like hoisted the sails and you like blew a gust of wind into them and then you're like, oh wait, never mind. You like filled my sails with wind and then you just took all the wind out. I don't care, now you asked it. So, if you scaled this up, the flip side, right? Because I mean, who knows? Maybe somebody 10 years from now is watching this YouTube video and they have that question. If you scaled this up to 10, any of these checkpoints around the circle create your 2 legs. That is your vertical and your horizontal distances. It's your coordinate location. So that's how this ties into the unit circle, is if we scaled it up to 10, those are the leg lengths. Those are your coordinates, essentially. Like literally, they're your X and Y locations compared to your unit circle. If the center of your unit circle is the origin, right, the center of the graph, these are literally your X and Y coordinates. So, with the angle of 35 degrees up here, we would relate to triangle 1, 2, or 3. 2. And then, since the hypotenuse here is 8, Great. Do I ever want just the answer? No. How we would deal with this here is this triangle's hypotenuse is 8/10 of the reference triangle. So we multiply our leg lengths by 8/10, right? We're just using similar triangles and that similarity ratio. We're going through these fast, so I'm really just hitting like one problem type from the different things that you'll see. So does anyone have a question about how to use the reference triangle and a scale ratio here? The other thing that I actually prefer doing is if my hypotenuse is 1, this triangle's 8 times my reference triangle. I think that's better, but that's just me, and I'm often wrong, so that's fine. Try this one on your own. First, ask yourself, what ratio are they asking me for? So WY compared to WX, what is that? Yeah, like short leg over long leg, right? You're right. It's adjacent. Oh, wait, adjacent over. Yeah, hypotenuse. So it's short leg over hypotenuse, right? Or adjacent if we look at the 70-degree angle. So from 70, okay, we're going to reference over here. Adjacent over hypotenuse, okay. Adjacent over hypotenuse. What should the ratio be here? Hey, look, it's simplified down to 1 like it's a unit circle. So, Now where we got to write more notes. Get that pen back in your hand. Well, fine. When people hear the word trig, almost always, and this feels to me like a very American thing, they're like, oh yeah, SOHCAHTOA. And then they open this door, right? And then you're like, oh yeah, what is SOHCAHTOA? And they're like, I just remember my math teacher saying SOHCAHTOA. And they don't know how to do trig. All they remember is SOHCAHTOA, because that was the catchy like little thing their teacher said, memorize this. So, write down SOHCAHTOA, but then I'm going to show you how you should actually write it down. Yeah, that's the other issue, thank you for asking that, I was hoping somebody would, is those people will even forget how to spell it, and then even if they remember how it applies to trig, if they don't remember how it's spelled accurately, they do it wrong. Here's how SOHCAHTOA should actually look in your brain. Because really, it should look like this. And really, what these people should be saying is, oh yeah, sine and cosine and tangent, which we abbreviate because mathematicians are efficient, into sin, cos, and tan just because that fit on the calculator buttons. Now I'm making that up. I don't know why that got decided to be the abbreviations, but it is. No, not like bad, not like, oh no, I killed someone. Like, no, not sin. Sine. So if you notice on the start slide today, I had typed out sine is S-I-N-E. This is cosine, so co-S-I-N-E. And then this is tangent. Now you'll learn a lot more about tangents when we start talking about the unit circle. What this really should look like is this. And that is your so part of SOHCAHTOA. Your ka, aside from if you go to a ka dealership up in Maine, no, they just have a weird accent when they speak. And when they say car, it sounds like ka. Gotta get in the ka. Cockies. You are, thank you. I seriously thank you. I appreciate that. Because what I said was wrong. Yeah, you're right. And the TOA part should actually be tangent of theta equals opposite over adjacent. Now, here's the other thing that a few years ago broke my heart when people took a map test, and I'm so glad that we're doing this today before you map test. All of this is worthless if your calculator's not in the right mode. It's like typing an entire paper and then switching the font to wingdings. Like, that's pointless. What we have to check is in your graphing calculator, or even in just your scientific calculator, what mode are we in? I don't know where my scientific yeah, here we go. So whether I'm in my graphing calculator or my scientific calculator, I can choose whether we're dealing with degrees, radians, or ignore the GRD thing. I don't know exactly what. That's gradient, I think, but we're not going to go into that. We need to be in degrees until we need to be in radians. Radians was that thing from the unit circle that I told you really briefly about, is the distance around that curved distance. That deals with radians. We're not doing that yet. Okay, so although I keep saying, like, here's where this applies, we're not doing that yet. So please make sure that your calculator is in degree before you start trying to do any trig, unless they're giving you radian values. Guys, on your map test today, they might, just trying to confuse you. If they give you a value, like, if they say on your map test it says, like, sine of radical 3 over 2, if you try to type that in, when you're in degrees, check it. Because this is a a thing from the unit circle, your answer comes out to be really, like, what? So check it. If I switch my mode, this is actually the right answer. Now, this was a bad example for me to use because they both come out to be small decimal numbers. But let's say it was a multiple choice question. And you do sine of radical 3 over 2, and this is not one of the options there. You're in the wrong setting, right? So that's the issue. When they give you degrees, like 37 degrees, you know you're in degrees. But if they give you something like this, you're not in degrees. You're in radians. If it doesn't have a degree symbol, it's radians. If you guys are about to ask, how do you know if it's radians? If it doesn't have a degree symbol.
Quick question. On app test, when they give you a little calculator, will they do it automatically, or will it just be evil not do it?
It should, I believe. You can check it, but what I'm more so talking about is end of course assessments, ACT and SAT, when you are using your own calculator. That's like, you care a lot more about the SAT than you do about your math test, right? And when you go to take, so when you go to take your SAT, you're going to have to take your own calculator. I'm not sure when it comes to the math test. Feel free to raise your hand in whatever room you're in, and like, if the calculator pops up and something seems wrong, feel free to tell the teacher or ask that question. We can help with any tech issues. We can't necessarily help you with. Yeah. Now, honestly, if the teacher in your math classroom asks if they think you're allowed to use a calculator or not, since math is just for us, I'd be happy if you want to use one of these. I don't care. So if they let you, if they ask the question up there of like, do you think I care? I do not care. I would prefer that you just go ahead and use one of these. Okay? So that's my personal preference. If they don't let you, don't get upset about it, because math doesn't truly matter that much. Realistically, guys, for you guys, I don't look at your math data. I don't. Sometimes I might at the end of the year when I'm trying to extend and if I cover all my content, it's not going to happen this year. But if I cover all my content, then I look at math data and I see, okay, what do they not know? What could we get into math 3 wise? But guys, from all my 7th graders, I look at their math data. Your high school teachers next year might look at your math data, but they'll care more about your spring math data than right now's math data. So there is a purpose to it, but for right now, this test, I don't really care. Huh? Because they want to know how far behind you are right now when we came back to school. They wanted to do this a month ago. Right when we came back in January, and we said no. We're like, no, they just came back to school. We need some time. Amar? And no, I have no idea. That'll be determined by which high school you go to, what honors or not. I would suggest that all of you take honors. That is a symbol that is also used like theta. I forget if that's actually beta or if that's a lowercase theta. Either way, that's indicating that that is our reference angle. So notice up here that I say the sine of B. So we are just going to practice setting up what would be the ratio of the sine of B for that triangle. So what is sine? Opposite over hypotenuse. Excuse me. So the sine of B, and we're not going to necessarily do all 3 for each of these. The opposite, the opposite over the hypotenuse, 4 over 5. (15 over 17). And 12 over 13. Notice that that's always going to be less than 1. Because if the hypotenuse is always your denominator, that's always your longest side. The hypotenuse, your denominator, is always the biggest number. So if you accidentally type in sine of an improper fraction, you will get an error. So now notice I can't actually type in sine of 4/5 and get the right answer. That's not what we're doing here. I will show you in a few minutes why we would do this. I did. My answer here is actually 53 degrees. Notice I'm not using sine. What am I using? Inverse of sine. That -1 power is always the inverse function. So that's actually the answer after we use algebra to solve. No, degree. If we're looking for degrees, we want to be in degrees. If we're looking for radians, we want to be in radians. If they give you the angle, look at what they gave you. Did they give you degrees? Did they give you a weird non-degree value? That's going to be radians. If they give you a funky number that doesn't have a degree symbol for an angle, it's radians. If they give you a funky number with no degree symbol for the length of the leg, that's just a funky number. You know what I mean? So cosine, what's cosine? Ca. Adjacent over hypotenuse. So 3 over, is this also always going to be less than 1? Yeah, so if you put it in your calculator wrong, it will tell you you're wrong. It just tells you like error. This can't be what you're trying to do. It literally says like, nope, you can't be trying to do this. It's not right. And tangent, notice this is the same triangles, but I switched up here to tangent. What is tangent? Opposite over a, ooh, wait, can tangent be improper? Yeah, so tangent can be improper since it does not involve the hypotenuse. How do we actually use this? Why do we actually use this? When we look at triangles, go ahead and sketch this triangle in your notes real fast. Like, it does not need to be pretty. I feel pretty, oh so pretty. I feel pretty and witty and gay. And I suddenly think the world is gonna go my way. I'm totally making up words at this point. La 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 la. Who's that pretty girl in that mirror there? What mirror where? Those are the words to the song, actually. We're looking for what side? Don't give me like A, C, A, but what side compared to our angle? Opposite, and we have hypotenuse. So we have to ask ourselves, which function uses opposite hypotenuse? Ding, 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 ding. So we're going to set up sine of our angle, put the degree symbol so we remember that we're in degrees, equals the opposite side over the hypotenuse length. And we can actually, because one side is a fraction, set the whole thing up like a proportion or like equal ratios. And we know to get rid of division by 7, we multiply by 7. So really, we're just going to multiply both sides by 7. You'll see in a minute. It makes more sense when it does not solve so nicely. And in your calculator, because practice this, I want to make sure that you're getting correct answers. Type in 7 times the sine of 40. If you are in degrees, because remember they gave us degrees here, you should get the answer 4.49. So really 4.5. Now, why did I put that 1 there? Well, first off, because I can. Because I can put any number over 1 and it doesn't change a darn thing. But in a situation like, not this one, the next one. But, yep, I'm almost out of time, so we might as well look at this. In a situation such as this, set up your trig ratio. Sorry, I need that little bar at the bottom to drop away. It's 3. I don't know why my taskbar won't go away. So we're still dealing with opposite hypotenuse. But what's different here? The unknown is in the denominator. If we remember one of the fun things that happens with proportions, we could cross multiply, divide out to solve, or if you remember like the trick here, what can we actually do to say h is equal to? They can just trade places. Because what the algebra shows us is if we have a over b equals c over d, and we want to find d, we can actually just swap these locations, and if this denominator is 1, it doesn't impact anything. So when we cross multiply this way, and cross multiply this way, and then divide to solve, h is actually 3 over sine of not 30, that's 20. So guys, these values, if you remember that little trick from working proportions, these values can actually just swap places because this is a 1. So then in your calculator, type in 3 over sine of 20. As long as you're in degrees, you'll get that your hypotenuse, which of course should be the longest side of your triangle, comes out to be 8.77. Any questions here? That's not the whites. Seems like go free. Oh, yeah.
About her, but I have no idea
Maria. I'm in love with a girl named Maria. If you haven't seen West Side Story, you really need to. It's like one of the most classic musicals, like American musicals ever. Like, it's like a Romeo and Juliet story because there are two competing like gangs called the Sharks and the Jets. And there's an epic scene that maybe I can look up very quickly where they fight and they snap and they sing and they dance and it's... Yes, they do also kill people. All right, check it.